Welcome to the course on power quality. Today we will discuss power quality improvement in wind energy conversion system. We will discuss with the outline just introduction to wind energy conversion system and of course, wind farm in India and power quality improvement in grid connected wind energy conversion system. Then we will talk about classification of grid integrated wind energy conversion system, in which we will talk about fixed speed wind energy conversion system and variable speed wind energy conversion system. Then we will talk about squirrel cage induction generator based wind energy conversion system, then doubly fed induction generator based wind energy conversion system and synchronous generator based wind energy conversion system, and then permanent synchronous generator based wind energy conversion system, and then synchronous reluctance machine based wind energy conversion system. And of course, like you can call it, the wind is the now second largest renewable energy source for generating the electricity throughout the world, and of course, in India also it is coming up big way. Well, so this wind energy conversion system convert the wind energy of conversion of kinetic energy of wind into electrical energy, and it has increased size, higher productivity, and enable wind energy to become an increasing competitive alternative to more traditional methods of power generation. And uncertainty in the main problem with wind production owing to the inherent predictability of weather conditions, and utilization of wind generation is generally rather low, with most in the 25 to 35% utilization area. And this is the typical block diagram of wind energy conversion system, where we have typically a wind turbine on the along with the generator on neckline, and with of course, we have a normally gearbox, because the wind turbine runs at very low speed and many generator runs at quite high speed, like a DFIG and induction squirrel cage induction generator. Normally they run at 1500 rpm, 15 to 800 rpm. So that is a 4-pole machine, we adopt it, and wind turbine certainly runs typically around 50 to 150 rpm. So that is the reason. And then we have a controller and power converter, which convert this variable, you can call it variable frequency output to typically to constant frequency, which can feed to the transformer, and then with the protection it goes to the grid. And of course, we have some time, not all the time, battery energy storage system for smoothing the fluctuations, typically the intermittency of wind energy conversion system. Well, the advantage of wind energy, you can call it wind power, it is a cost effective, cheaper than solar, and wind creates the job. It is clean fuel source, it is sustainable, and wind turbines can be built on existing farms or ranches and a smaller land requirement when compared to the solar or hydro. And it can be built of course offshore and fluctuates lesser than solar. So, challenges of wind power is wind power must still compete with the conventional generation sources on a cost basis, and good land based wind sites are often located in remote locations far from city where the electricity is needed, and turbines might cause noise and aesthetic pollution, and wind plants can impact local wildlife, and of course, it has an intermittency issue, and of course, offshore tire are more expensive, and premium of onshore sites are saturated, and worldwide capacity reached 650.7 gigawatt by the end of 2019, and total installed wind capacity in Asia reached 290.6 gigawatt, 44% of the global capacity, and in India the wind power installed capacity reached 38.26 gigawatt up to 31st October 2020, and India has the 4th largest wind installed capacity in the world. India has the 2nd highest wind installed capacity in Asia, and these are the typically you can call it potential of wind energy typically in India. Total of you can call it the potential is 302.2 gigawatt with the different potential in different states typically of the India, and these are the typically you can call it wind products overview in megawatt turbines from geophysics, then GE Energy, Siemens, Vestas, RE Power, Multibird and Enercon, and they have a different they are using different generators like permanent synchronous generator, doubly fed induction generator, squirrel cage induction generator, then high voltage doubly fed induction generator, doubly fed induction generator, permanent generator, and electrical excited synchronous generator. So, you can see that they are using both kind of induction machine, and they are using permanent synchronous generator as well as the conventional single pole synchronous generator by Enercon, and the unit size of course varies from 2 megawatt, it has gone even typically of 6 megawatt by Enercon. and well, you use of course the, I mean only in PMSG we use the gearless as well as conventional synchronous gearless, but otherwise they use the different stages gears to match the speed, and you will find all are using power electronics converters, I mean for different purpose. The reason of power electronics converter is that you will be able to have the generation with the maximum power tracking at variable speed, and you are able to generate around 50% more energy using the variable speed wind generation system, and that is the reason that lot of power converters, I mean either even in case of DFIG or other machines are there, like I mean also. So, there are in India, like there are for this major power plants are located in all these typically 8 so many plants starting from 1500 megawatt, then 1064. So, it goes to typically even like the plant of typically of 14 major plant up to 50 megawatt capacity are already installed in India, and these are the typical some photographs of typically varying of 1500 megawatt plant with the capacity of, you can call it sizes varying from 200 kilowatt to 1650 kilowatt. And then you have a of course develop the Suzlon Energy developed the Jaisalmer wind park, the second largest onshore wind project of 1064 megawatt. And then we have a Banawali in Maharashtra 528 megawatt, of course in 2 stages, I mean like installed by WECS turbine of 1650 kilowatt, and then Suzlon model of 1250 kilowatt, and then of course Micon put another total power of 5 turbine in typically of 3 megawatt like, and these are the different parts of this plant of 528 megawatt. They have a different, I mean you can call it different stages also. Then another is 278 in Maharashtra, the plant with the typical capacity of Suzlon and Enercon. Enercon of course use the conventional synchronous generator, and then typically they have been in different part with different typically generators of different rating, and then this is another plant of 259 megawatt with the Suzlon, I mean like typically in different areas, and they are again 100.5 megawatt in Madhya Pradesh, like where you have a typically WECS turbine of 1500 kilowatt, I mean diameter of 87 or so with the capacity of your 100.5 megawatt. And then you have another in 56 megawatt, 56.1 megawatt in Karnataka. I mean this is we are talking about different states. Now coming to typically now power quality improvement in grid integrated wind energy conversion system. I mean typically they have to be integrated to the grid, like I mean like wind energy conversion system connected to the grid with normally with the transformer, where the other loads and other generation and typical loads are there. So there are challenges like typically in the for the grid integration of dispersed wind generation, and that is highly variable and wind power typically injected into the grid, and increased penetration of the wind energy, and electrical weak distribution network like radial structure and large R by X ratio distribution line, and heavy reactive power burden brought by the induction generator. And we have a other power quality related issues in this, and typically is like a this is the first fixed speed wind generation, I mean like still Siemens is manufacturing that. So, you have with the gearbox a machine, normally 2 machine of squirrel cage 4 pole or 6 pole are there, and for reactive power we use the capacitor and put the power to this. Of course, in spite of typically with the gear 2 machines of 4 pole and 6 pole, so some concept of you can call it maximum power is used corresponding to 2 speed, but of course, it is limited. So, we still call the fixed speed configuration, but otherwise, so this has a like a typically gearbox normally, because squirrel cage machine is used of 4 pole and 6 pole, which runs at around little bit more than 1000 rpm and 1500 rpm. So, to bring the wind turbine speed of very low 150 to 150 rpm to order of that about more than around 1000 rpm to more than 1550 rpm, you have to use the gearbox, and then they have a soft starter also and capacitor for power factor correction. This is of course the induction machine used for variable speed generation. Again we use the kind of gearbox, but we use of course double converter. So, it is run with the, you can call it like a normally variable frequency induction generator by controlled by this machine converter, and it puts the generated power to the DC link, and from DC link this grid side converter put to the grid. So, here it is more important that we worry about the typically that this power is fed without power quality problem. Even there may be a power quality problem in the grid like. So, why we are using in spite you are using this converter more than twice the rating of the power which you are generating, because processed twice, but since wind power generation is like able to generate around 50% energy from very wind blowing by putting a maximum power tracking algorithm, and that is the reason we are able to even process the power with the couple of power converters, whole power is. Similarly, synchronous generator, we have a like a again the gearbox, of course, in silent pole machine, Analcon is not using the gearbox, otherwise all cases there are again double the converter and put to the grid. Then people have a permanent, typically you can call it permanent synchronous machine, again double converter and put to the power to the grid. And of course, with the because you are having a converter, you can have a very wide speed range, a high efficiency with a smaller, typically you can call it wind turbine blade diameter, and do not require any external excitation typically, because it is a permanent excitation here. And then DFIG, this is considered one of the best machine for wind power generation, and the reason being that the major amount of the power is directly processed stator to grid without only to facilitate the variable speed. We have this rotor side converter and stator side converter. Rotor side converter is responsible for maximum power tracking by controlling the torque in vector control, and by generating the reactive power we have a unity power factor on stator, so that there is no reactive power burden on the supply system, and the DC linkage maintained by the grid side converter. However, the grid side, if anything else you need the reactive power, the grid side converter can provide that also. So, this and moreover it suits, of course, you use the gearbox, because machines with the 4 poles runs around typically 1000 rpm to 2000 rpm, so that you can have a MPPT for that. So, around 75% manufacturer are manufacturing this, you can call it the this is doubly fed induction generator, like because the speed range is enough from 1000 to 2000 rpm for this wind power energy conversion system. And moreover, here the process power is hardly, typically if you are going to let us say 1000 to 2000 rpm with the synchronous speed of your 1500, you only process around 30 or 30 to 35% power. The power converter rating is hardly 40% of each. So, it is less than even both the converter rating is not even 100%, where the other cases you have a 200% of power converter, and here major amount of power is going to be through directly connected to stator like. And of course, you can, so variable speed from 70 to 130% of synchronous speed, and of course, you need the gear and reduced rating of bidirectional back to back converter, or typically sometime we have even a transformer here also, but otherwise this transformer also serve the purpose like. So, main advantage are simple and low cost, cheap and low maintenance, and major drawback is low wind energy conversion efficiency, of course, sometimes and power fluctuation and high mechanical stress on turbine. So, most installed nowadays are variable speed drive. So, coming to squirrel cage induction generator based typically grid integrated energy conversion system, this is typically that we have with the gear and we have one converter, you can have another converter and connected to the grid, and of course, for a small unit you can connect a battery, and you can have a local load also here. So, you can improve the power quality on the grid side, and moreover you can have a feature with islanding mode also to feed this local load with the, because the battery can take care even the power variation from the solar as well as from the wind like also. And they typically that how you are regulating the how you are doing MPPT of the wind generation, and how you are typically having the DC link voltage control, like from there how you are having a control of the DC link, typically from the battery you are regulating the DC link voltage from that. And these are typically the load compensation that you are, as we discussed already in many times, that we are able to extract the fundamental from here from the load, and then we are able to have averaging. We have a wind feed forward term, we have a solar feed forward term, and then we are able to get the grid current. We have a template of the grid from voltage template, and then we have a reference grid current, we have a sense grid current, and we are able to control the grid side converter like also. And this is of course machine side converter control for maximum power tracking. Typically normally, even we are able to use sensorless control most of the time in motor control like. So, that maintain the typically with the vector control of the machine speed corresponding to, because you have a reference speed corresponding to MPPT, and you have a feedback speed either by estimation or by your sensing, and then you get the torque from which torque producing component, and from flux you get the flux producing component, and you are able to convert 3 phase currents from this angle which called flux angle, and able to have a reference current, then with the feedback current you control it. So, machine currents are also close to sinusoidal as well as the grid current also control close to sinusoidal. So, power quality improved is improved on both the side like. And this is typically the kind of, you can call it the in your typically when grid is recovered, how it is synchronization take place by floating the angle of the your grid side converter towards the grid, and then once it closes, comes to close, you can close the switch, otherwise it's operate in islanding mode, like with the proportional resonant controller which have a steady state R0 with the even sinusoidal varying current, and you have a typically the local load current, and you are able to have a switching of this converter like, and still maintaining the voltage and frequency across the load like. And they typically even the your voltage are typically are on the grid side typically on the distorted, still you are able to get the filtered voltage, and then you use in the typically in the control for controlling purpose like also. So, we can call it like control of grid mode operation. The positive sequence grid line voltage are estimated from the sense voltage. So, from the sense line voltage we are able to estimate positive sequence voltage, and then we are able to get a typically from these voltage we are able to get phase voltage from line voltage from positive sequence which are balanced and sinusoidal, and then we are able to estimate the template in phase with the these phase voltage. And we are able to get like a typically the fundamental current of the corresponding to the load to extract from this and typically from the load current, and this is the typically the load current, this is the fundamental extracted current, and of course, the constant which you use in this algorithm, this is the typically coming from this algorithm, and these are the 4 typically B and C phases, and you are able to take then feed forward term for solar and feed forward term from the wind, and you are able to get a reference grid current like from this relation from template and the amplitude of the grid current like. So, that controls typically, and where you have a load current average, and then you have a reference grid current where you have a positive sequence of load current, then you have a DC link voltage control output, that also the kind of loss is there, and then you have a PV feed forward term, and you have a feed forward term of the wind generation. So, you get the amplitude of grid current from which you have calculated the reference current. Coming to islanding control, you have used the normally proportional resonant controller, because that can have a steady state at 0 even with the sign varying voltages like. So, you have here the typically inverter current from the voltage typically from the voltage error, and you are having a voltage error with the reference voltage and typically the sense voltage for all 3 phases, and this is typically the you can call it the setup upon which. So, you can cite the grid current, you have a load current, and you have a grid side converter current. So, you can have a grid current and grid voltage are sinusoidal and power quality improved, in spite you are able to improve the power quality of the local connected load, and these are the typical harmonic analysis corresponding to your in this case like. So, you have a typically the in B here the grid current typically the grid power, and you can have a the quantity of the grid voltage grid current all the quantity here with the P and Q of the grid and power factor of the grid on closer to sinusoidal, and these of course, even you have a kind of distorted voltage, still you have balanced sinusoidal current also, and you have a quite good TAD typically of the voltage and current on the when you have load current TAD quite high, still you have a grid current TAD quite typically less than 5% here. These are voltage TAD in typically in RN mode, and this is the voltage TAD in grid connected mode like, and this is typically the power corresponding to the you can call it the solar generation, and then this is dynamic performance when grid connected as solar irradiation changing in this hybrid system. When the load is removed, grid current is increased because now load is not consuming the power. Similarly, when you start the load, the less current is reduced on the grid, but still you can call it voltage and current remain in the phase like typically. And here of course, if battery is not there, how it is the system is working, still it can work very well, and with the load removal, load addition, how the performance is there of the your typical this system like also. So, load addition, load removal and load addition performance here like. And then typically you can call it grid is appearing here after few cycles, grid is synchronized, the system is synchronized to the grid. So, grid current is start appearing. So, you have a very smooth switching of this distributed energy, you can call it energy conversion system to the grid without any tangents, and similarly you can have a like when this grid disappears, still you have a smooth operation of your typical system like without any much problem like. So, now coming to typically another wind generation system we call doubly fed induction base grid and grid integrated wind energy conversion system. So, we have a here the DFIG with the gear which already, and you have a rotor side converter, stator side converter, you have a synchronized switch here, and you have a typically the grid here like also, and you have a local load also, and certainly we have to improve the power quality on the grid side. in this case. And the very beauty of this is what we already discussed it, the converter rating is quite low, hardly around each converter have a 40% rating to 80% rating, compared to in previous case you have a 200% rating of the converter, and you can still have a unity power factor on each stator side. So, this DFIG suits to one of the best way, typically you can call it like for wind power conversion system like. And this is the typically your algorithm for your typically for estimating the angle and frequency. I mean like in this system for estimating the your from the sense voltage also, and this is typically for your control for rotor side converter, which not only takes typically your MPPT. I mean this is your maximum power tracking algorithm you take care. It also takes care even a kind of generate the desired reactive power, which may be 0 for unity power factor on the stator, which give the rotor D axis current, and typically and the Q axis current is generated with the help of your vector control for maximum power tracking. And then you have a like a voltage, but it is a voltage control. Normally we use 1.8 kilohertz switching frequency for the rotor side converter. So, we have a normally voltage control after getting this. So, this vector control quantity of rotor voltage we are convert from the slip angle into the 3 phase, and then we have a rotor side converter control, and this is typically your grid side converter control. I mean which again we can have of course, here we this have to responsibility of the DC link voltage control, I mean reference DC link voltage, and this, and you can generate even desired reactive power also required for the at the grid side like also if you really need. I mean, and that is virtually again from vector control we are able to get a 2 axis current. I mean we can have a reactive power, otherwise we can have only the active power for regulating the DC link voltage, and these are the grid reference current, and we have a typically the sense grid current, so we have a getting signal for that. So, that is double. So, the rotor side converter control is typically between stator fluxes and DN. We normally use the vector control in DQ because this quantity becomes DC, and design of the PI controller, you have a number of PI controller here becomes easier, and this is typically what you can call it the your D axis current and Q axis current of the stator from the rotor D axis and Q axis current, and then this is typically you can call it like a corresponding to your flux angle, stator flux angle, and you have a typically the currents corresponding to from your sense current to typically alpha beta currents, and then you are able to use the typically the transfer function for the typical control from these for here for alpha beta like also. And grid side converter again you have a similar filter for typically getting the your eliminating the your even the harmonics or unbalance into the current with using this filter like. And these are typical system which are developed in the laboratory for the power quality improvement on the grid side from using the DFIG, and these are typically the rating of the DFIG for which system is developed, and these are you can clearly see the grid voltage, grid current. I mean like of course, these are intermediate signal corresponding to your stator side, and these are when the wind speed varying how it is the typically the different quantity are changing like as you are wind speed increasing and wind speed decreasing, and you can clearly see the rotor current. I mean it passes through synchronous speed. So, it runs at exactly synchronous speed as a synchronous generator, and it changes very smoothly over a wide range, and but the stator you can call it the you have a grid voltage already stable, and you are able to generate the varying power with that. And these are of course, the intermediate signal which you are estimating typically the position as well as the you can position angle as well as the your typically the speed like, and you are able to have typically the fluctuation how you are estimating the speed. Those are the typical kind of intermediate signal also in the system like I mean also and during the change also. And when you have a nonlinear load, I mean the stator side converter is able to work as a active filter like, and you have a grid current typically I mean grid current is still sinusoidal, and with the sinusoidal grid voltage in phase with the out of the phase because it is generating the power and depends on the speed, and these are typically again the your intermediate signal of the control like so. And this is typically the sudden change of the load when you have a load change, how the complete system is changing corresponding to that like, and these are the 3 phase voltage and currents of, and the total harmonic distortion here in the current is typically less than 5%. I mean the typically on the grid side where the load current is quite high, order of 26% or so. So, that is about DFIG. Now, coming to synchronous generator with grid integrated system with typically the Enercon is still using, but here we have a let us say again the wind energy conversion system with the conventional synchronous generator, but we are using voltage source converter, machine side converter here with the vector control, again with the sensorless, and of course, we use the maximum power tracking algorithm for the wind power generation, and then we put on the DC link and which feeds to the power to the grid. Of course, you can have a local load for compensation also, but the grid current sinusoidal and unity power factor. Of course, you can use the energy storage here, so that the fluctuations either of the typically of the wind generation or the load is not reflected on the grid. So, you can feed even the constant power to the grid like on. And this is the typical algorithm that you have a fundamental extraction from the your load current, you have a wind feed forward term, and you can feed the fixed power from the given power from the battery also. So that is coming from there. So, you have a net you can call it the weight corresponding to generating, and you have a that is the amplitude we consider on the grid current. You have a template of the grid current and you have a reference grid current, you sense the grid current. So, you are able to put this power to the grid with the sinusoidal current and balance current at unity power factor, because you are generating in reference to the typically in the grid voltage. So, two line voltage are sensed and which are converted into phase voltage, and from phase voltage we generate template as well as the amplitude of the voltage like. And this is the typical algorithm corresponding to machine side power control. So, there are typically you can call it the we have a by sensing the DC link and 2 generator current, we are able to have from the switching the estimation of speed and position. We have a position and speed estimated, and from speed and from this we are able to get per turbine observed maximum power tracking algorithm, which gives the wind speed. We have typically estimated, you can say this is estimated speed. So, we have a speed controller to have indirectly implementing the this maximum power tracking, which give a torque producing component, and we have a flux producing component for unity power factor here for conventional synchronous machine, and of course, 0 sequence 0. So, this DQ is converted from typically from position angle to into 3 phase reference grid, typically the synchronous generator current, and we have a sense synchronous generator current for vector control, and which generate typically the getting signal for this maximum power tracking for the wind power generation machine side control. And this grid side converter, we sense the typically the line voltage and convert to phase voltage, then we calculate the amplitude and we calculate the template on grid side converter, and we extract certainly the fundamental component from the load current. That is typically the load current we extract from using this filter, and we average it for load balancing, and then this is the feed forward term for the wind, and we have a feed forward term from the battery and wind, and this the load. So, this we get the weight corresponding to grid current, and then we have a reference grid current multiplying the weight and this weight and from the template. So, these 3 phase grid current are compared with the sense grid current, and we generate the gating signal like. This is typically switching of machine side control for maximum power tracking, how the maximum power tracking algorithm is utilized for the estimating the speed, reference speed for wind power generator, depending upon the similar to like what we do even for even the solar in the same manner. And then we are able to have a from reference speed, we are generating from maximum power tracking algorithm, and we have a estimated speed, and we are able to have a torque producing component from using the PI controller, that is the torque producing component of your synchronous machine. And we have a DXS component corresponding to unity power factor, and that algorithm is implemented, and these are the typical result of, you can call it the typical grid voltage, grid current, like here, and the typically estimated position, and typically the DC link voltage, load current, but the grid current, load current is non-sinusoidal, but grid current is sinusoidal, and these are the typically the signal corresponding to reference current and grid current like. And these are, you can clearly see here the TAD of the in islanding mode is a TAD 2.4%, when the your load current TAD is 19.7% like. Is able to improve the power quality, and when you are having a typically varying the here the load, like load change, when you have a load change, like the reference load current for intermediate signal is change here, when you apply the load it increases, and accordingly the your reference grid currents are changing like typically like. And these are, you can clearly see the TAD of the grid current is 4%, where the voltage is also only, you can call it 1.8% like. And these are variation when the wind speed increases. So, the grid power is also increases, load power remains. So, because the wind generation have increased, and how the grid current is increasing because of the increased wind generation like. And then when you have a decrease, typically the battery start typically charging and discharging depending upon the your power generation from the wind generation like. And these are the battery performance. You can clearly see here how the battery is feeding the power and discharge, and here the your typically you have a TAD of the voltage of 4.4%, where the low TAD is 22% or so. Now, coming to another wind energy conversion system using permanent synchronous generator. Why we are taking this permanent generator? Because it does not, it is a you can run even at without gear also. That is the one of the major benefit, offers the highest efficiency like. So, you have a typically permanent synchronous generator which can run without the gear if you design really at low speed, and then you have a your machine side converter and grid side converter to feed the power to the grid, and you can have a typically here also the sensorless control. I mean typically for maximum power tracking algorithm using this your sliding mode observer like which use here. So, for machine side control again we use the vector control, and for grid side converter we of course typically maintain the DC link voltage from this, because from the wind generation how much power we are generating, that virtually the grid converter will be able to know by control of DC link voltage, and then we are able to have a load compensation also, and to put the grid current at constant you can call it sinusoidal and balance current like. And this is typically you can clearly see the how the estimation is there of the angle as well as position. So, we are typically estimating the fluxes, we are sensing the current and DC link voltage. So, you can see the estimated speed and position here like and these are typically the variation in wind energy, wind speed, how the you can call it the even your current of the generator are varying and position is changing like, and how the other your typically the your 3-phase current of machine are changing with respect and power is changing. So, this is the typical setup on which this algorithm is completely tested. So, these are the position, and you have a current corresponding to the of the generator for a varying wind speed of 12 meter per second and 8.4 meter per second. Estimated speed and estimated position for a given wind velocity, and then the of course, the current of the PMSG, and then typically you are having a here the again the your DC link voltage and your inverter current for 3 phases for 2 different speed variation here, and then how the you can call it power of the wind generator, you can call it the typically of your reference current wind speed, your estimated speed as well as the wind speed is varying. So, that is the effect of dynamics you can call it like. Now, coming to the another generator which have recently come very much by Siemens and NEB, which called synchronous reluctance generator, which have higher efficiency than your induction skull cage induction generator, because there are no losses. So, this is typically the wind generation with the gearbox, and you have a machine side converter, grid side converter connected to the grid. Of course, it feeds at unity power factor sinusoidal, but you can compensate by this converter the local load also. After that, whatever is the fed local load, that can go to the typically the grid like. So, here you have again concept of maximum power taking from the wind speed. You have estimated speed from your DC link voltage and the 2 currents. You are estimating the speed, you have a reference speed from maximum power taking algorithm. So, you have a speed controller, your torque producing component, and from this error we are able to get your 2 vector control quantity, which convert from the position which you estimated to into 3-phase current of the generator, and from sense current of the wind generator you are able to get getting signal for the machine side converter. And these are the typical algorithm from DC link voltage, how we are getting the 3-phase you can call it the alpha beta voltage, and we are sensing the current. So, we are getting alpha beta component of the current, and from which we are calculating alpha beta component of the flux, and we are estimating the torque like, and then we are able to estimate the position as well as the speed of this like or for that like. So, that is typically from the phasor diagram you are able to get different angles, and these are of course, the you can call it like a typically the estimation of the point of common coupling voltage we are sensing, and from this observe we are able to estimate again here alpha beta, and from which we are able to go PL. So, we get the typically frequency and phase for the kind of synchronization as well as for the control like. So, this is typically grid current reference, and we have a sense grid current, and we control this converter, and this is the typically the you can call it load current extraction which is required typically. So, we have a DC link voltage control, we have a wind feed forward term, and we have a load local load feeding. So, we get a reference grid current here amplitude multiplied the phase. So, we get 3-phase you can call it grid current, and we have a sense grid current. So, we give the gating signal over the switches like which even you can synchronize with the these signals like that operates in typically in islanding mode like. So, these typically the algorithm that you are having a DC link voltage controller from PI controller, then you have a typically corresponding to the wind generation. This is for load compensation, and that is your reference grid current. Multiplying the template, you get the 3-phase current. These are the template calculation from the sense voltage, phase voltage, line voltage. And these are typically the observer from which we are getting the position and speed from this observer, and these of course this is tested. So, you have a typically you can call it here the your voltage TAD and say load TAD, and here the you can call it the grid current TAD. These of course converter current TAD also. And then this is the dynamics when you have a change in the your wind generation. As wind speed increases, wind generation increases, and these are the typical currents like on the grid side which increases, and grid voltage remains the same like also. And during this is typically the enlarged waveform for typically you can call it the variation on the load demand and load changes. Like a one phase load is removed, that is the reason from square waves go to typically quasi square wave to go to closer to like a, and here the load is you can call it is removed, here load is applied. So, these are dynamic performance because of the load change here like or load increase. So, and how the different quantity of the complete load is removed, load is added. Typical synchronization. This is standalone mode, this is distorted grid voltage, and here it is the synchronization. You are having grid voltage here, typically grid is appearing here and grid current is starting. So, it takes 4 to 5 cycles to grid synchronization. So, these are typically the different wind energy conversion systems for power quality improvement. Let us come to the numerical problem. So, coming to first design a 2 megawatt wind turbine for a doubly fed induction based wind energy conversion system, considering a rated speed of 12 meter per second with optimum speed ratio of speed of blade at tip angle of 7.2 and maximum coefficient of power is 0.44, a density is 1.224 kg meter square. Assume a minimum slip of minus 0.3% up to which the DFI is 50 Hz 4 pole is operated at maximum power point. And typically here the solution, the value of the blade radius and gearbox have to be calculated for the design turbine. So, this is the wind turbine power extraction, where these are the wind velocity, the diameter of the wind, and this is the output power with the coefficient of so from here in putting all the data relation, we get the typically the here the you can call it the radius of the wind turbine from the for given power like of here about 2 megawatt like so here, and coming to with the 0.3 minus 0.3 slip for 50 Hz 4 pole DFIG. So, operate at MPPT, tip ratio should be optimum. So, from this slip relation we are able to get the you can call it rated speed from this, and we get the here the speed of the machine 204.2 radian per second, and the speed ratio can be calculated from the radius and the rotor speed and wind velocity and coefficient. So, we get from here the expression becomes for this coefficient, it comes from putting the value, it comes 87.04. Now, coming to second example, a 50 kilowatt wind turbine, rated wind speed of 12 meter per second, maximum coefficient of 0.44 and the air density of 1.224 kg meter cube is coupled to a synchronous generator for wind power generation, and the generator is indicated to 3 phase 415 volt 50 hertz utility grid using a back to back connected power converters. If the system is operating at 8.5 meter per second, then calculate the RMS current injected into the grid, assuming negligible losses and power injected into the grid at unity power factor. With the typical system that we have a synchronous generator with a converter, and this is a grid side converter, this is a machine side converter and connected to the grid. And for a 50 kilowatt, this is the power relation in terms of wind velocity, radius of the wind turbine and coefficient, power coefficient, and from this we can find out the radius of typically of the wind turbine. And from this same power relation for another speed, we are able to get the power for another speed 17.78 kilowatt, and assuming the lossless negligible losses, we are able to get the grid current from power and from this voltage, that is the typically grid current of 24.73 ampere. So, coming to a third example, a squirrel cage induction generator based 250 kilowatt wind turbine with the back to back connected converter is integrated to 415 volt 50 hertz supply. To smoothen the wind power irregularity, a 48 volt battery energy storage system is integrated at the DC link of the voltage source converter through a bidirectional DC-DC converter and control scheme for the wind energy conversion system designed to provide a smooth power of 100 kilowatt to the 3-phase grid at all time. Calculate the battery current when the wind turbine generates the power of 160 kilowatt. Also calculate the current injected into the grid. Assume the unity power factor operation, grid side and negligible losses. So, these are typical system. We have a squirrel cage machine with a gearbox, wind turbine, and then we have a machine side converter. We have a battery which is smoothen the power, which required the this is generating typically 160 kilowatt, but we want 100 kilowatt on the grid side. So, these are typical total system. And coming to the solution part, the incident with speed enables the squirrel cage generator to generate 160 kilowatt power, that is given, and power flow to the grid is 100 kilowatt. So, we know the battery power from Pg minus PL, so it comes minus 60 kilowatt, and the current injected to the battery from power divided by voltage, so it is 125 ampere, and the grid current from power divided by at unity power factor root 3 into your grid voltage RMS, so it comes 139.12 ampere like. So, coming to fourth example, a multifunctional 50 kilowatt permanent synchronous generator based wind energy conversion system is integrated with 415 volt 50 hertz 3-phase grid using the back to back connected voltage source converter, and the complete wind energy conversion system is connected with a linear load which is drawing 35 kilowatt power at a power factor of 0.8. Calculate the voltage current kVA rating of the grid side voltage source converter of the wind energy conversion system to provide reactive power compensation. So, this is the typical system. We have a wind turbine with permanent synchronous generator, and we have a this you can call it the machine side converter, and you have a grid side grid fed converter fitting there, and we have a local load fitting this grid side. So, that is the system. So, we have a line voltage 415 on the grid side. So, phase voltage becomes 239.6, frequency is 50 hertz, and active power drawn by the load is 35 kilowatt. So, reactive power drawn by the load is we can find out from 0.8 lagging power factor. So, this comes 26.25 kVA. At the grid side voltage source converter is used to reactive power compensation. So, reactive power through the grid voltage source converter is this typically the load reactive power, and assuming the negligible losses, the active power flowing to the grid. So, grid fed voltage source converter is the typically the power 50 kilowatt, and we can find out the grid side voltage source converter P Q square plus P square. It come putting the value 56.47 kVA, and voltage rating of course of VSI is same as the grid voltage, that is phase voltage 239.6 volt, and the current rating we can calculate from the power divided by 3 kVA divided by typically from 3 into at unity power factor with the power, so 78.56 ampere. So, coming to fifth example, in the question 4, if the doubly fed induction generator is used in place of magnetic synchronous generator, calculate the kVA rating of the grid side voltage source converter of the wind energy conversion system to provide reactive power compensation. Assume a slip of minus 0.3 per unit for the DFIG rated current. So, this is a typical system. We have a with a gearbox DFIG, and we have a of course, the converter on the double converter on rotor side, and the stator side connected to the grid here, and of course, we have a typically local load. So, here the given that the Vs equal to 415 by root 3 239.6 50 hertz, and active power drawn by the load is 35 kilowatt. So, we can calculate the load reactive power P1 tan phi, the typically active power 35 kilowatt into tan inverse cos phi. So, it comes 26.25 kVA, and the grid side VSI is used for reactive power concern. So, reactive power of the grid side converter is same as the load reactive power, and doing negligible losses, the active power flow through the grid side converter of DFIG rated equal to the power flow of the DFIG equal to slip power rated. So, it is 0.350 15 kilowatt, and the kVA rating of grid side converter will be your reactive power square plus active power square, that comes 30.23 kVA. So, for PMSG based WECS it was 56.47 kVA, here the reduction of the converter is to only 30.23 kVA in DFIG. So, coming to sixth example, a 60 kilowatt synchronous reluctance generator for wind energy conversion system connected to 3-phase 415 volt 50 hertz utility grid through the back to back connected voltage source converter, and wind energy conversion supplying a linear load of 4 kilowatt and 2 kVA reactive power, and the grid side voltage source converter ensure that the grid is always operated at the unity power factor, and grid voltage source converter losses can be assumed to be 5% of its power. Estimate the load current and the grid current under rated wind speed. B, calculate the grid power factor and the phase shift in the grid voltage and with respect to the phase voltage. This is the typical system. We have with the gearbox, the synchronous reluctance generator with the machine side converter and grid side converter, and we have a local load here which connected at the point of common coupling, and this is typically the grid line. So, coming to solution part of energy conversion system is operating at rated condition. Thus, the net power supplied by the wind is 10 kilowatt, and considering the losses 5%. So, net VSC active power is 0.95 times 10. So, it is a 9.5 kilowatt. Load power, load active power is 4 kilowatt. So, net power going to the grid is 9.5. This power minus the typically this load power. So, it is 5.5 kilowatt. Since the grid voltage is 415 line RMS. So, current in the grid can be calculated typically from here your S divided by line. So, you have a 4 typically for the load and 2 kVR. So, you can find out the load current 6.22 ampere, and then we can find out the grid side the current to be computed for the grid. So, you have a P because we are maintaining unity power factor divided by root 3 line voltage. So, from putting the value we get 7.65 ampere active current, and it is noteworthy that the only 3 phase active power is considered for calculating the grid side line current, and this is because the voltage source converter is ensuring unity power factor operation all the time. And since the VSC control scheme ensure that the grid always operates as unity power, the grid line current are always in phase with the corresponding phase voltage. And however, in this case, since the power fed is being fed to the grid at grid power factor is negative, thus the grid power factor will be grid power is negative. So, that is the power factor will be -1. So, owing to the unity power factor of the grid voltage source converter supply the total reactive power of 2 kVR. Since the active power fed through VSC is 9.5 kilowatt, the phase shift in the VSC phase currents with respect to the phase voltage can be computed from the reactive power divided by active power. So, it comes like 11.89 degree. So, now coming to summarize the typically for wind energy conversion system. So, basic power quality related changes in wind energy conversion system have been discussed, and different configuration of fixed speed and variable speed wind generation system integrated with the utility grid have been presented, and control scheme simulation results and experimental results of power quality improvement in grid integrated system comprising the SCIG generator of wind energy generator has been presented, and control scheme simulation results and experimental results for the power quality improvement grid integrated WDFIG phase have been presented, and control simulation result and experimental result of and power quality improvement grid connected synchronous generator based wind energy conversion system is also given here, and control scheme simulation result and experimental results of grid connected palm grid synchronous generator based wind energy also presented, and control scheme simulation and experimental result and for power quality improvement grid connected synchronous reluctance generator has been presented, and these are the some of the references on which this presentation is made, and thank you very much.